Hello and welcome to Mr. Alvarez's virtual chemistry classroom. Today we'll be covering our fourth honors topic, relative strengths of acids and bases. Our aim for today is, how can we determine the relative strength of specific acids and bases? Let's first talk about strong acids versus weak acids. A strong acid will give up an H+, a hydrogen ion, easily, which means it will dissociate completely, 100%. For example, hydrochloric acid, HCl, is a strong acid. So when it's dissolved in water, it breaks up completely into H+ ions and Cl- ions. On the other hand, we have weak acids. They hold on to their H+ ions. Few molecules dissociate. For example, hydrofluoric acid is a weak acid. HF, when it's dissolved in water, I'm going to draw a double arrow because while there will be some H+ ions and fluoride, F- ions, most of the HF will not dissociate. So you'll see more HF in solution than you will see H+ and F- ions in the solution. And weak acids will conduct electricity very poorly. Let's take a look at the diagram. Here we have a diagram representing a strong acid on the left and a weak acid on the right. Now, if the acid was represented as HA, where H would represent the H+ ions after it dissociates, and the A would be the negative ion, the anion, after the acid dissociates. You'll notice here in this first box, all you have is H+ and A-. This is a strong acid, it completely dissociates. However, in the weak acid solution, you notice some H+ ions and some A- ions, but for the most part, the HA did not dissociate. This would be considered a weak acid. It did not dissociate fully, and this would not conduct electricity well. It would conduct a little bit of electricity, but not too well. Here we have a strong acid shown in a different way. The reactant side, we have our HA. The H is represented by the small purple dot, and the A is represented by the big blue dot. After the HA, the strong acid, is dissolved in water, you have complete 100% dissociation. We have a bunch of H+ and a bunch of A-, but in the product side, there are no HAs like we had in the reactant side. All the HAs completely dissociated. Therefore, this is a strong acid. On the other hand, we have a weak acid. Once again, in the reactant beaker, we have all HAs together, but this time when we dissolve the HAs in water, most of them do not dissociate. They stay together. Since we have such a low rate of dissociation, this is considered a weak acid. Very few HAs broke up into H+ ions and A- ions. A weak acid, while it will still conduct electricity, will conduct electricity very poorly. And that brings us to the purpose of today's lesson. We can write dissociation constants for both acids and bases. If we're writing a dissociation constant for an acid, we would represent that by Ka. And if we're writing a dissociation constant for a base, that would be represented by Kb. For the model problem, write an equilibrium expression for the following dissociation of an acid. This is going to be very similar to what we did during the equilibrium unit. We are going to write, instead of an equilibrium constant, we are going to write a dissociation constant. So since we have an acid, it's going to be Ka equals the concentration of products over the concentration of reactants. Now, just like when we did the equilibrium constants, liquids and solids do not factor into the equation, so we get rid of them. Only aqueous and gases are represented in the equation. So now that we got rid of our liquid and there are no solids, products over reactants, that is going to equal the concentration of H3O plus times the concentration of ClO4 minus, the brackets once again mean concentration, over the reactant, in this case, the concentration of HClO4. There are 6 different strong acids. They are perchloric acid, which is HClO4. That's the acid we just wrote the dissociation constant for. Hydroiodic acid, HI. Hydrobromic acid, HBr. Hydrochloric acid, HCl. Sulfuric acid, H2SO4. And nitric acid, HNO3. Now, when I look at this list, I see 3 out of the 6 acids that have something in common. Do you think you could see the pattern? Just in case if you didn't see it, the pattern I see is that 3 of these strong acids consist of a hydrogen and a group 17 element, a halogen. Now, there is one group 17 element missing from this list, fluorine. HF, hydrofluoric acid, is a weak acid. As we saw earlier on. Now, the reason why hydrofluoric acid is a weak acid is because fluorine is so electronegative. It has an electronegativity of a perfect 4.0. It is going to hold on to that H plus really tightly due to its high electronegativity. It's not going to let go. Since it holds on to that H plus really tightly, it doesn't completely dissociate, which makes it a weak acid. Now let's talk about strong bases versus weak bases. Just like a strong acid, a strong base dissociates completely in water. It dissociates 100%. Group 1 metal hydroxides are all strong bases. For example, you have sodium hydroxide, lithium hydroxide, potassium hydroxide, so on and so forth. And some group 2 metal hydroxides. So calcium hydroxide, barium hydroxide, and strontium hydroxide are also strong bases. A weak base, only a few ions will dissociate. For example, ammonia, NH3, is a weak base. In the top diagram, we have sodium hydroxide, a strong base dissolved in water. When sodium hydroxide, NaOH, dissolves in water, it dissociates completely into Na plus and OH minus ions. It is a strong base. However, NH3, ammonia, is a weak base. When ammonia is dissolved in water, you get NH4OH, NH4 pluses, and very few OH minuses, very few hydroxide ions. Remember, according to the Arrhenius theory of acids and bases, a stronger base will dissociate into a greater concentration of hydroxide ions. So therefore, more hydroxide ions, the stronger the base. The fewer the hydroxide ions, the weaker the base. Before we move on, let's talk about conjugate acid-base pairs. Please remember that a strong acid will have a weak conjugate base. Here we have hydrochloric acid, a very strong acid, and when it's dissolved in water, here water is acting as a base, the acid becomes the conjugate base, which is Cl minus, and Cl minus is a weak conjugate base. Strong acid will yield a weak conjugate base, and a strong base will yield a weak conjugate acid. Strong acid, weak conjugate base. Strong base, weak conjugate acid. Let's practice writing some dissociations of acids and bases. The directions state use a single arrow for a strong acid or base, and use a double arrow for a weak acid or base. Remember, a strong acid or base will dissociate completely, whereas a weak acid or base will not dissociate completely. The first one, HCl, is a strong acid. It will dissociate completely. So we have HCl, a single arrow, since it's a strong acid, goes to H plus and Cl minus. NaOH is a strong base, so it will also dissociate completely. So we have NaOH, single arrow because it's a strong base, goes to Na plus and OH minus. Let's jump down to E, HC2H3O2. Acetic acid is a weak acid. So when we write that, we're going to use a double arrow. So HC2H3O2, double arrow, H plus C2H3O2 minus. Let's jump down to letter G, copper hydroxide, a very weak base, so we will use a double arrow for the weak base. So we have copper hydroxide, CuOH2, double arrow goes to copper 2 plus, there's two hydroxides, so we're going to write 2 OH minuses. Once again, strong acids get a single arrow, weak acids and bases get a double arrow. Practice problem number 5 states, the H plus concentration of a 0.10 molar solution of cyanic acid, HCNO, is found to be 0.0010 molar. Calculate the Ka for cyanic acid. Now, before we can calculate anything, we must write a dissociation equation for cyanic acid. So we have cyanic acid, HCNO. We draw a double arrow because cyanic acid is a weak acid. And that will dissociate into H plus and CNO minus. When we write the Ka, the dissociation of the acid, that is equal to the concentration of the products over the concentration of the reactants. We plug in our products. We have H plus times CNO minus. Those are our products. Over the reactant, there's just one, the concentration of HCNO. Now we can plug numbers in. So it says the H plus ion concentration of a 0.10 molar solution of cyanic acid is found to be 0.0010 molar. So the H plus ion concentration is 0.0010 molar. So we plug that in. 0.0010 molar. Now, it does not tell us what the concentration is of CNO minus. However, when HCNO dissociates, it's going to break up into equal amounts of H plus and CnO minus. So if we have 0.0010 molar of H plus, we must also have 0.0010 molar of CnO minus. Divided by, it's a 0.10 molar solution, so 0.10 molar of HCnO. Now we just very carefully punch these numbers in the calculator. When you divide molarity by molarity, the units cancel out. So you're just going to be left with a number, no unit. So when we do 0.0010 times 0.0010, we of course get this very small number, 0.0000050. So let me just check, 1, 2, 3, 4, 5, divided by 0.10. So our Ka is going to equal, when you divide this number, divided by 0.10, excuse me, you get 1, 2, 3, 4, 0.00001 as our answer. Remember, just like when we did equilibrium constants, a Ka value of less than 1 will give us a weak acid. Problem number 7 is a little bit trickier. Problem number 7 states a 0.0050 molar solution of butyric acid, HC4H7O, has a pH of 4.0. Calculate the Ka. So first we're going to write the Ka expression. Ka equals products over reactants and our two products are H plus times the concentration of C4H7O2 negative 1 over the one reactant, the concentration of HC4H7O. Now, while we have the concentration of the butyric acid, the HC4H7O, we do not have the concentration of the H plus or the C4H7O2 minus. So let's plug in what we do have, 0.0050 molar in brackets. What we do have is the pH. Remember, pH equals the negative log of the hydrogen ion concentration. To find the H plus concentration when given the pH, in this case it's 4.0, what we do is we take 10 and we raise it to the negative pH, which is to the negative 4.0 in this case. So we have the H plus concentration of 10 to the negative 4.0. Molar, of course. And remember from the last problem, when butyric acid dissociates, it dissociates into equal amounts of H plus and C4H7O2 minus. So if we have 10 to the negative 4th molar of H plus, we must also have 10 to the negative 4.0 molar of C4H7O2 minus. So now, when we plug it in, 10 to the negative 4th times 10 to the negative 4th will give us a very small number. Remember, the molarities cancel out. So we have 0.1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, and a 1 over 0.0050. So let's finish this off. Divided by 0.0050. And we get our Ka is equal to 0.0000001, 2, 3, 4, 5 zeros and a 2. Or you can write that as 2 times 10 to the negative 1, 2, 3, 4, 5, 6th power. Two times 10 to the negative 6 is our Ka value. Problem number 8 is probably the trickiest problem that we will do today. Problem number 8 states, determine the OH minus and the H plus ion concentrations of a 0.20 molar solution of formic acid. The Ka is 1.8 times 10 to the negative 4th. So let's write our Ka expression. Ka equals products over reactants, the concentration of the products over the concentration of the reactants. And let's plug in. We have H plus is product number 1 times HCOO minus is our second product over our reactant HCOOH. Now, we have the Ka and we have the concentration of the formic acid, HCOOH. What we do not have is the concentration of the H plus or the HCOO minus. So let's plug in. Our Ka is 1.8 times 10 to the negative 4th equals H plus concentration times HCOO minus concentration over 0.20 molar. The very next thing we need to do is we have to get the H plus and the HCOO minus by itself. So we multiply both sides by the concentration of the HCOOH. So multiply both sides by 0.20 molar times 0.20 molar. So when we do that, we get 0.2 times 1.8 times 10 to the negative 4th. So we get 0.000036 equals H plus times HCOO minus. Now remember from before, since the HCOOH is dissociating, it's going to break up into equal concentrations of H plus and HCOO minus. So what we can do is we take this number, the 0.00036 molar, and make that equal to x squared. Because once again, these two will be equal, and anything times itself is that number squared. So to solve this, we take the square root of both sides. So x, in this case, will equal the H plus ion concentration, will equal 0.006 molar. So that will equal our H plus ion concentration. But we're not done. It also asks for the OH minus ion concentration. So now that we have the H plus ion concentration, what we must do next is take the negative log of the H plus ion concentration to determine the pH. So our pH will equal to the negative log of 0.006 molar. So our pH will equal negative log 0.006. Our pH will equal to 2.2218485. Let's round that to significant figures. Our original numbers have two significant figures, so our pH is equal to 2.2. Now we must find the pOH. I'll write it up here. pH plus pOH is equal to 14.0. Well, if our pH is 2.2, and the pH plus pOH must equal 14, if we subtract 2.2 from both sides, we get the pOH is equal to 11.8. Now, to find the OH minus ion concentration, so the OH minus ion concentration is going to equal 10 to the negative 11.8. 10 to the negative pOH. So if we do that, 10 to the negative 11.8, we get a hydrogen ion concentration of 1.584893192 times 10 to the negative 12th molar. Once again, we do two significant figures. 8 is higher than 5, so that 5 rounds up to a 6. So our OH minus ion concentration is going to equal 1.6 times 10 to the negative 12 molar. Of course, this is an acid, so the hydrogen ion concentration is going to be much higher than the hydroxide ion concentration. Thank you for joining Mr. Alvarez's virtual chemistry classroom. Today we took a look at the relative strengths of acids and bases. We compared strong acids versus weak acids, and strong bases versus weak bases. We also learned how to write dissociation equations for acids and bases, and we also learned how to calculate dissociation constants for those acids and bases. Thank you again for joining us. I hope you learned something today. Please join us again soon.